Go. All right, so we have a solution of this and a solution of this. I may or may not have written the AQs after these when I originally did it, but I think we were referring to aqueous solutions of these things. So anyway, we have aqueous solutions of these two substances. We are mixing them together. Write a net ionic equation for a reaction that may occur between the species involved here. Okay. Now remember, this question happened immediately after we learned how to write a molecular equation, a complete ionic equation, and a net ionic equation. And I said, ultimately, you guys need to get to the point where you can look at pairs like this and get to the net ionic equation for one that, if one exists, quickly. So, what are my possible products? Calcium carbonate and sodium nitrate. Will either of those remain in solution? The sodium nitrate will remain in solution. Okay? Will the calcium carbonate precipitate? Now, I picked this product specifically. What is calcium carbonate? No. Twice. Chalk. Does chalk dissolve in water?
I said that it's a precipitate. When you put a solid piece of chalk in water, it doesn't dissolve.
Right.
So it is.
Yes, precisely. So, no. So, this will precipitate. So what is the net ionic equation that would represent that precipitation? Go.
But calcium and then
No. Next.
Wait, you're asking what? Did you do the calcium carbonate and then the arrow?
No, it'd be the other way around.
CCVA.
No.
Plus.
The calcium ion.
I was getting there.
Plus.
Carbonate ion. 2 minus.
There we go. Okay. Next, any questions so far? Okay, next one. What are my possible products? And?
I have a question. This is kind of a minor one, but can you put the plus signs in there?
We're just, again, what I'm saying is, absolutely.
I just want to make sure.
No, absolutely. What I'm saying is, I'm trying to get you guys to get to the point where you can get to this from this. Now, currently, we're not incredibly good at this yet. So I'm trying, the only reason I'm writing these down right now is for everyone to recognize what the actual products are that we're considering. Does that make any sense?
Yeah.
Ultimately, we need to be able to go from here to here. Right now, I'm kind of doing this as a little side thing. But if it helps you, absolutely do that. Are there any that are going to remain in solution? Are either of these products going to remain in solution? Why is that? Yeah, acetate salts are always soluble. So that means if a precipitate were to form, it would have to be the silver chloride. Now, if you've looked at the, those of you that have taken the time to look at the solubility guidelines that were in the book, okay, I know some of you at least are aware that they exist, maybe have looked at them a little bit. Honestly, almost every chloride is also going to be soluble. There are 3 exceptions. Anyone want to name one of them? Lead. Who said lead? Because were you the one that noticed that lead's like an exception for just about everything? Yeah. So lead Lead chloride would be one that would precipitate. Turns out silver chloride is one, and no, barium chloride is soluble. Good try, though. No, aluminum is also soluble. There was one more. It might be mercury. I think it's mercury. No, calcium chloride is incredibly soluble. Most of you use that on your sidewalks in the winter. Well, everything that we're discussing up here is a salt. Everything that we're discussing up here is a salt. All right, so anyway, turns out the silver chloride will precipitate. So, what would be the net ionic equation for this precipitation? Silver ion plus chloride ion yielding silver chloride. Yes, Emily?
Do you have to write, like, coefficients? Because, like, technically,
yes.
It would be Cl2.
Oh, no. No. Yes, you write the coefficients. However, to form silver chloride, how many silvers are there? You see what I'm saying?
Yeah.
So each silver chloride is only going to be, or one silver and one chloride.
Okay.
No, I know what you're saying. I currently don't have an example of what you're talking about. I can come up with one.
Yeah,
I will come up with one.
Okay. I was just thinking.
No, that's a good point. Can I do that one now? Can I do the thing now that she's asking about?
Yeah.
Okay, so if I gave you, because now are we starting to get a little bit better idea of what's going on here? Is it coming together a little bit? I know we're not like perfect at it yet, okay? But I think you're at least trying to see what the goal is and how to get to the goal. Let me do an example of what Emily's talking about. I guess I'll do it over here. Let's go with and yes, this will definitely be what we're looking for. Okay, take 52.3 seconds or so and look at that and see if you can come up with a set O products and or ideally a net ionic reaction or net ionic equation. What are the products?
Sodium chloride.
Yep. And
Iron hydroxide.
iron 3 hydroxide. Whoops. Will any remain in solution? Obviously the sodium chloride, okay. Turns out the iron 3 hydroxide will precipitate, okay. So, and this is, I hope, what you were asking about, Emily.
I think it is.
So, we take some iron 3 ion, we take 3 hydroxides, and that is what you were talking about, to form the iron 3 hydroxide.
So we don't have to use, like, in the CuCl2, we don't have to use all the Cl to get our net ionic equation, our net equation.
No, because for the only reaction that occurred,
Okay.
this was the reaction.
Okay.
I know what you're saying,
Yeah.
and that's actually going to get addressed. It was going to get addressed today. It's not going to anymore. I just know we're not going to get there.
Yeah.
Okay, moving on. And finally, the last one. What are my potential products? And will either neither of them remain in solution. What's that? Both of them. Neither one will precipitate. So what's the net ionic equation? There is none. There is no reaction. All 4 ions are going to remain in solution, floating around like the little dots that I put up on the board the other day independently, which is exactly similar to the question number 7 on the quiz that you guys took yesterday, but we'll get to that tomorrow. By the way, we're going to spend the first part of tomorrow, because we get the bonus time tomorrow, going over that. And there's definitely needs to be some going over on that, okay? It's not stuff that can't be fixed in no way whatsoever. Your brains just haven't quite accepted the whole mole thing and things floating around in solution, okay? You'll get there. They're just not all quite there yet. So anyway, that's tomorrow. Next. All right, so does anybody feel a little bit more comfortable with the process here? I think you're starting to get a little bit more comfortable with what's going to precipitate or what is not going to precipitate, mainly? Okay. All right. Then, let's continue. Are we on, well, I don't know the page numbers anymore. Types of chemical reactions? Or did we already do that? Oh, we already did that. Stoichiometry of precipitation reactions. Awesome. Here we go. Seriously, and this paragraph that it says right after the little bullet point, materials foundation for all, much of the inorganic, this is almost the rest of our entire class. This is, doing what we're going to be doing is the rest of the class, for the most part. It's a little bit, okay, with the exception of periodic trends, with the exception of drawing Lewis structures, okay, and gas laws. But really, all the rest of it is based on what we're about to do. Yeah. Okay. Now, let me see. So, as it says, materials foundation, blah, 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 it combines the concepts of molarity, solubility guidelines, balancing equations, and limiting reagent calculations. Okay? All of that stuff is from here on out. So, example number 1. I'm going to briefly refer to the quiz because I've graded nearly all of them. Here's the progress that was made. You guys may remember me kind of getting on this huge soapbox and saying, do not use grams unless you're given grams or you're asked to find grams. Other than that, eliminate grams, right? Because almost every one of you was desperately trying to work grams into the whole thing, okay? There has been progress made. More people did not use grams in their calculations. There are still a few hangers-ons that are desperately trying to squeeze grams into a place that has no business having grams, okay? What we're doing today will be a great example of that. We're rarely going to use grams. The only time you use them is if you're given them and you got to get out of them, or you're asked to find them. Here we go. First example. Calculate the mass of solid precipitate. Are we going to use grams?
Yep.
There we go. Produce 125 milliliters of 0.2 molar silver nitrate is actually blah, 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 blah. Write and balance the equation. Ready, set, go. Extemporize. That was the word I was looking for. Sure, if you want. How was vacation, Renee? Is this the yearly family vacation, or is this a different thing? Oh, don't you guys usually do something like right at the end of the year, right in the middle of exams every year? Okay. Yeah, I've had enough of you now to know this. Are you the last one? Really? Okay. What do we have here? Silver nitrate, sodium sulfide. I'm hoping you guys all came up with that. What? You did the net ionic?
Yeah, because it's asking
Okay, so here we go. So, what does it take to make that?
Well, it's two silver ions and one
Sulfide.
sulfide.
Okay, and actually I'm kind of glad that you are forcing this issue, because another thing that you guys are going to find really soon is the AP will only show you, not all the time, but a lot of times the AP questions will only show you the net ionic equation, okay? So what if you were only given the net ionic equation? And I'm going to go ahead and erase this. What if you were only given the net ionic equation, or sorry about that, you were given the net ionic equation, which, okay, will happen now because they're not making you guys do all this predicting of products as much anymore, okay? Now what are you going to do? The question will remain as it is, and it will say something to the effect, is added to excess sodium sulfide solution according to the equation below. And this might be the equation that's below. Yes? Sulfide. Oh, I know that. What I'm saying is, what are you going to do with the rest of the information that's provided? Now, ultimately, what are we trying to find? The mass of the precipitate. How many grams of that? What's that? Okay. Well, which of these things were we which of these things were we provided with as far as information is concerned? Yeah. Is that what you're going to say, Gracie? And how much was there?
There was 125.
125?
125 milliliters of 0.2 molar silver nitrate.
0.2.
Molar. 0.0 molar.
There we go.
Of sodium nitrate.
Yeah. Of silver nitrate? Of silver nitrate.
Yes.
Is this silver nitrate?
No.
Yes, it is.
Yes.
Why? What's the nitrate ion?
Oh, it's the
Start. Yes, there we go. It's a spectator ion. We don't care about it because it's going to keep floating around in the solution the whole time.
So it's there.
It's there. It's just not there. The only thing we care about is this. Go ahead, Joe. Are you working it through? Oh, sorry about that. Yeah, my bad. Whoops. Okay, so there's the silver nitrate. How much sulfide were we given? Excess.
Yes.
So now what are we going to do?
Take the 0.125 liters times 2 molars to get the moles.
Okay, so we're going to convert to moles, okay? Now, up until a few days ago, whenever we converted to moles, we were given a mass. We had to find the molar mass or formula mass, convert to moles using the mass, correct? Are we given a mass? No, then don't go to mass. Stay away from the mass. Convert to moles using the molarity equation. So, as we know, molarity is moles over volume. Therefore, moles is equal to molarity time volume. We have both of those things. So we go 0.200 molar. Gracie, this is why I was making you say this, because I knew significant figures are going to matter. And this represents 0.125, or 1/8 of a liter. 1/8 of 20.2, whatever. Half is 1, half of that is 0.05, half of that is 0.25. Correct me if I'm wrong on that.
Yeah, you're right.
We good?
Yep, I just like one.
I gotcha. And now that's moles of silver nitrate, okay? And what's the stoichiometry? Silver sulfide, okay? That look good? And now we just need the mass of the silver sulfide, which 107.87 times 2 plus 32.06, whatever that comes out to be.
247.
If anyone wants to verify that, that would be awesome. 247.81. And you're consistently pretty good at those, so we'll believe you. Well, I never believe anything, so nicely done. Unless I can verify. And I don't know, when you do the math, I ended up getting 3.10 grams. Where many of you used to go, or would have gone, and more of you are getting better at that, is you guys would have done some weird thing over here and found the molar mass of silver nitrate and somehow tried to incorporate that into the thing. Does that sound familiar? Notice we don't need to do that because there's our moles. Not too difficult. Any questions before we move on? Next. Oh, well, now we have a thing. A thing I've been waiting for. What mass of iron 3 hydroxide? Is that where you guys are? Okay. Are we going to use molar mass? Or formula mass? It says what mass of iron 3 hydroxide. Are we going to use a formula mass of that? At some point in time, okay? When 35 milliliters of 0.25 molar iron 3 nitrate is mixed with 55 milliliters of 0.180 potassium, blah, 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 determine, oh, and then, is there another sentence after that? Determine and concentrate. Okay, for the immediate time being, let's ignore that sentence because we got that's a whole nother can of worms. Okay? But the everything up to that point, let's walk through this. Can we go directly to, just out of curiosity, a net ionic equation from here? What would that be? Well, that's the product, yes? You said iron 3 plus 3 hydroxides? Would everyone concur with that? Some of you aren't because you're not quite there yet. I just want to show this to you. Don't write this down because once again, like on an AP question, the additional sentence would have been according to the equation, either above or below, wherever they happen to put it. Okay? Now, where did this come from? Don't write this out. I'm just showing you where it came from. What were the two substances? Was it sodium hydroxide? Potassium hydroxide. Okay, so it was KOH plus iron 3, what was it? Nitrate. Obviously producing iron 3 hydroxide plus potassium nitrate. Blah, 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 blah. That's where this came from. But many of you guys are getting to the point where, because I've asked you to try and get to that point in your head. Okay, I just wanted to show you where that came from. All right, next. Do I know anything about either of the two? Oh, obviously we're looking for this. What mass of that? Am I provided with information about either of the other two species? Okay, what do we know? Gracie.
You have 5 milliliters.
Okay, tell me what species we're referring to.
On the iron.
Okay.
You have 35 milliliters of 0.250 molar.
There we go.
And for the hydroxide, you have 55 milliliters of 0.180 molar.
What is this? Limiting reactant problem. Because we were given the amounts of both things. Would you agree? Now, remember that when we first started doing stoichiometry this year, I said there was like 3 different ways. There was the way that I taught how to do limiting reactant problems. There was the way Mr. Homan taught how to do stoichiometry or limiting reactant problems. Who else was there? A Cotting in here? It was you. Okay. And I don't know how she taught. I actually don't. Okay. And then I showed you a third way where we just found out the moles of each thing. That's why that thing is so powerful. Watch this. That's the way I'm going to use with this. Okay. So let's convert this to moles. How do we do that? Molarity times volume. That is your new. Before, up until a couple of days ago, you guys were all very good at converting masses to moles. That's one of the reasons why you're sitting here in this class today. You were very good at converting grams to moles and moles to grams. Okay? This is the new way to convert to moles. So, 0.18 plus you, 0.055 comes up with something. Now, watch how I set this up. And let's do iron. And over here, I'm going to label this hydroxide. And here we have 0.25. And this one we can do in our head. This one maybe not so much. 17, 8.5. And did anyone happen to do this? Go ahead. 0.0099. And that's hydroxide. Hold on. No, heck no. No. Okay, no. You just walked right into the trap that so many students walk into at this point. This is how much hydroxide is present. Well, we're not done yet. Now, according to the balanced equation, how much hydroxide do we need? 3 times as much as the iron. Do we have 3 times as much hydroxide? In fact, we have less than the amount of, no, we don't. But barely, slightly more than what we have of the iron. Would you agree? What's my limiting reactant? Hydroxide. See how easy that is? We haven't done a single stoichiometry. We kind of did a stoichiometry problem, but we did it in our head. We already know the limiting reactant. Awesome. Let's find out the amount of product. How are we going to do that? Go ahead, Gracie. We're going to take the 0.0099 moles of hydroxide ion, multiply it by, what's that? 1 mole of iron 3 hydroxide for every, Gracie, there you go. There's a reason why I called on you. There's your .0033, by the way. Okay? Your brain had already gotten there. Now what do I do? For the first time, we're going to grams. Would that be correct? Do you have it? What do you got? Okay. I was just checking. 8.8, you say? And so now we can do this one relatively easily in our head. 1/3 of 106 is 34-ish, 33, 34-ish, but it's going to be a little bit over that, 35, 36-ish. Now we got to move our decimal point over. How many places, though? Because remember I said 1/3, but you know this is so we got to move it over 2 places. So 0.35-ish. Did anybody do it? What'd you get? 3.35. Say this again. 0.35. There we go. Grams of iron 3 hydroxide. Not too bad, huh? Now, I'm going to say, if this were an AP question, this might have been 0.2. They may have given this as, say, 0.06. Do you see what I'm saying? This could have been a multiple choice question easily. And then maybe the compound was calcium carbonate, which has a mass of like 110. You know what I'm saying? So you could, or maybe something, what is it, has a mass of 100? No, wait, calcium carbonate is right around 100. So they would have given you compounds in which you could have done the estimations pretty easily. But other than that, what do you guys think of the process? Not bad. I mean, you already know how to do limiting reactant problems. You know how to convert molarities and volumes to moles. I think you're starting to like this idea of what I'm doing here to figure out which one's limiting. Okay? And so there you go. Now, would you like to know the answer to, or how to figure out the answer to, question number 7 on the quiz yesterday, in which you had a mixture of 2 ionic compounds that were both soluble in water? Okay? Well, that leads us to the next part. Determine the concentration of all ions remaining in solution. Now, let's make a list of ions that were initially in solution. They were. Don't all shout out at once. It drowns. You guys kind of cancel each other out. Iron 3 was in there, was it not? What else? Hydroxide was in there. Potassium was in there. And nitrate was in there. Are any of those ions no longer present? Christina? Well, let her do it. You're saying the iron is no longer present as an ion. You're saying it's no longer present as an ion still floating around in the solution. Do you concur?
Yeah.
then that would be unfortunate. Yes, it did precipitate. But remember, the iron came from the iron nitrate, which was the excess reactant. What's that? There's still some left. Some of it went here. Some of it's still floating around. You get it now, yes? Some of it's still floating around in solution because it was the excess reactant, okay? That's the hard one. We're going to ignore that one for now, okay? We're not going to ignore it, but we'll come back to that one. So we know this is there. Is there any of those remaining three that are no longer present in solution? Hydroxide, because it precipitated and it was the piece that was part of the... In fact, it was the hydroxide that limited the amount of product we could make. The hydroxide is no longer there. See ya. How much potassium is there in terms of moles? Relatively speaking, more than, less than, the same. The same, because potassium was one of the spectator ions, correct? How much nitrate's floating around? The same, because once again, it was a spectator ion. Would you agree? Now, Anthony knows what to do from here. Well, now he does. Let's worry about the potassium first. Whoops. Whenever you put an ion, or whenever you put a species in brackets like that, that means concentration of. Obviously, which concentration term are we using? Molarity. Okay, so when we see the potassium ion in brackets, our brains should be saying molarity of potassium ion. So what is the molarity of the potassium ion initially? Well, the molarity was originally 0.18. Is it still 0.18? No, it is not. Is it greater than or less than 0.18? Less than 0.18. Why? There's a greater volume because we added the two together. So in the middle of the question on number 7, yesterday's quiz, it said, is a mixture of. In order to acquire a mixture, you have to mix. We've already covered this, right? Okay. So, how many moles of potassium are present? 0.0099. Yeah, 0.0099. Same as the hydroxide, because it was a 1-to-1 relationship, right? What's the volume that 0.0099 moles is in? 0.09. Because we have to add the two volumes together. Okay, so here, I know. I got a defective beaker over here. There we go. Okay, so now, in one of them we had 35 milliliters. Let's go orange. In another one we have 30. Whoa, that was 55. 35 milliliters. Okay, we add those two together. What do we get? 90 milliliters. Does this make any sense? We add the two together, right? So instead of these little things floating around in 55 milliliters, and these things floating around in 35 milliliters, they are now floating around in 90 milliliters. Would you agree? The same amount of particles are there. They're just floating around in a larger space. So their concentration is going to, as Joe said earlier, decrease, whatever this comes out to be. Does anyone have that? I do. Oh, go ahead. What is it? 0.11. And obviously, what are we going to do with the nitrate? The same kind of idea. Okay? Now, how many moles of nitrate are there? 0.0085, because remember that came with, but times 3. And Gracie, that's where the thing was that you were trying to do earlier. We will pick up from there tomorrow. Let's make it Monday to answer Avery's question from 32 minutes ago. Avery's question was, when is the assignment due? And I just said Monday. Monday, Monday, Monday.
So, for the answer to number 7, was it supposed to be in molarity then? Or?
I can't remember. Yes!
Okay. Because I did the ion